So let us discuss the solution for end semester examination. So first we will solve question number 2. Here you had to find out the Jacobian matrix for this quadratic element, for which the local coordinates are given in this picture. The shape functions were provided, and then I also told you that imagine node number 1 to be at the origin of the global coordinate system. So you can generate the coordinates for other nodes. So let us see what will be the real solution for this. So okay, so first what I have done in MATLAB is I have written all the shape functions. So, and I have defined eta as, so first you do is you define symbols. So I have defined eta as n and zeta as w, because I don't have Greek letters in MATLAB. And then I have written down all the shape functions. So S1 is the shape function at node number 1, and S2, S3, S4, S5, S6, S7 and S8. So these are the shape functions, and then I have described the partial differential. So if it is with respect to eta, which is w here, then differentiation of the shape function 1 with respect to w. And so I have done it for eta, and I have done it for zeta, and then I have done it for eta. Then I have defined the global coordinate system in a very laborious way. There could be better ways of doing it. So nevertheless, we have x1 to x8 and y1 to y8 values, and then I put xx is equal to ni xi's, so that is that. And similarly I have defined y's, and then I can calculate the components of Jacobian as del x by del zeta and del y by del zeta and del x by del eta and del y by del eta. These will be the components of the Jacobian matrix, and this is what the Jacobian matrix will look like. It's a long matrix. So if you see, it goes on. So this is the first element of the matrix, and it's not ended, so it is going till here, and then the second component and third component and fourth component. And then what I do is I replace the values. For zeta I put 0, because I told you to calculate the values at the center or centroid of the element, so you can put the values as 0. So I replace the value of zeta with 0 and eta with 0, and then so I did that here actually. And then so once I replace zeta, then I have only eta terms, and then I replace eta also by 0. So then the Jacobian matrix is this. The determinant of that matrix is -3/2. And then you can calculate from this, you can calculate the B matrix, you can calculate the A matrix. It should be very simple. Most of you have found determinant to be 1. So your first term, so what you have found the Jacobian was, so your Jacobian is this. You found this Jacobian. It can happen because it was a lengthy calculation, so you might have made some mistakes. Some of you are getting zeros, a lot of zeros, and also in differential many of you have made mistakes. So I have done it on paper also. So there is less mistake if you multiply the terms before finding out the partial derivatives. So in the shape function, for instance, here you should multiply this first before doing the differential and then do the differential. So when you multiply, then a lot of terms, not many of terms, but some of the terms will cancel out, and then it will be also easier not to do differential like a chain. You can do differential piecewise, element wise, and that decreases the amount of mistake. And the second thing is, you could have used a programming language like MATLAB. It could have been easier, there was no restriction on that. Nevertheless, so of course there will be step marking, because I have not seen so far any right solution. And let us now discuss the other part of the question. So this is done. Question number A and B is done. Then question number 1, you have to write an algorithm for any computer program to find von Mises stress for general values of stresses. So let us do that. So what you can do is, you can begin with initial values of stresses in any program. So you can write S11 will be given, so let us call it S11 old is equal to some value. So you will have old values of, so you can write Sij old values are given. Then what do we have? So then we have to calculate the Mises value based on the old values. So Mises value, in order to calculate that, we have to find out the eigenvalues, the principal stresses, or you can use sigma ij's with the direct formula of the shear stresses and normal stresses. So what I will do is, I will just write for finding out the principal stresses. So for that I have to simply write, so step 2, well, actually it is step 1, is to find the eigenvalues of the stress or old stress tensor. So old stress tensor, I believe this also can be done in MATLAB very easily, but in other programming languages you will have to write a different kind of program. So let me write the old matrix is equal to, let me give some value, or maybe I have given some value here in the second part of the question. So I have sigma 11 500 500 200 and 5.0. so I have 500, then sigma 22 is 200. So these are, no, I have sigma 12 which is 50, sigma 12 which is 50, and then I have sigma 22. So sigma 21 will also be 50, and then because it's a symmetric matrix, then I'll have 200 which is sigma 22, sigma 23 will be 0, and sigma 31 will be 0, sigma 32 will be 0, sigma 33 will be 0. So this is basically a plain stress condition because you don't have stresses in the z direction. So if I look at the matrix, so this is my stress tensor, and if I have to find out the eigenvalues, I believe the syntax is, so let me write principal stress is equal to, can I just write eigen, or should I write I think, I don't know, I don't remember, maybe I can see what it is. So I is the identity matrix. Okay, so maybe I should write eigen. Is it a function? I don't think so. Let's see. Yeah, what did I write? Unrecognized. Oh, they already have a function. Oh, eig is the syntax. Okay, So MATLAB is so good. Okay, so if I do that, then let's get busy in calculating the eigenvalues. And now it is calculating. So you have three principal stresses values here. So the minimum principal stress is 0, which means obviously because in z direction we don't have shear stress, we don't have normal stress, shouldn't get principal stress. So then I have sigma 1 is equal to 508.11 and sigma 2 and sigma 3. So now I have these three values. So I can, this was not required, this calculation was not required. So here you can simply find the eigenvalues of the old stress tensor, and then step 2 will be what? Step 2 will be to find out the value of the Mises. So you can simply write, so instead of this I write Mises or S Mises is equal to some constant, so 1 by root 2, and then you have 1 by root 2, and then you have S1 minus S2, so this should be in bracket, into S1 minus S2 whole squared, and then again let's simply copy. This was also not required, you could have just written sigma I minus sigma j, summation of sigma I minus sigma j. So sigma 1 minus sigma 2 whole squared plus sigma 2 minus sigma 3. Sigma 3 is not there, so this reduces, but anyways that condition was not there in the part A, so here it should be general. And then you have sigma 3 minus sigma 1 whole squared to the power 0.5. so this is my Mises value. This is very straightforward. So write the computer program to find out the one Mises stress. Okay, now in continuation we have to go. So here what you have to do in the part B is we have to put a plasticity criteria, find the new value of stresses. So first we have to check whether it is going in the plastic deformation or not. If it is going, then what will be the next value of the stresses? This is what we have to do in the second part of the question. So so I have taken the initial stresses already in MATLAB, calculated the principal stresses, and then you have to find out you have to check for the plasticity, and here also you have to write the algorithm only, or you have to calculate also. So you have to find the new value of stresses, you have to find it. Okay, so let us do that. So what did we do? So we have principal stresses here, then Mises will be equal to 1 divided by square root 2. I can simply write 1 by 414 into, then I have to write 508 point, or can I write principal stress is a vector, right? So principal stress is a matrix, control X. So if I write prin stress 2, yeah, okay, so this is working. So I can write stress 1 minus, I have to write 1 like this, and then let us just copy this thing, and here I don't have to write 3 minus 1 because no. So okay, so let us see. So principal stress 1 is 0. 1 is 0, so this will be simply minus of principal stress 2 whole squared, and then I have 2 minus sigma 1 minus sigma 2 is done. Then I have sigma 2 minus sigma 3, so that I can write, so sigma 2 minus sigma 3 whole squared. Okay, so do I no, okay, is that, and then sigma 3 minus, so sigma 2, sigma 1 minus sigma 2. Oh yeah, then sigma 2 minus sigma 3, and then sigma 3 minus sigma 1 will be sigma 3 only. So I'll just write sigma 3 and I'll put a square to this. So I'll put a square to this, close the bracket, and then give it a power of 0.5. So my Mises value is 444.47. So my Mises value is 444.47. What am I doing? Okay, and then, oh yeah, I told you this was 50. Okay, so current iteration was 440. So initial value of stress is, Mises value is 440, right? So then I will just write the plasticity criteria, and here, so this in the computer code this will be commented, but it's not a computer code. So here what I have to do is Mises old is equal to 440, Mises new, well, it's not Mises new, it is the Mises, oh, so in the one iteration before, so it is actually I minus 1. I minus 1 is 440, and that was also the first yield point, and now Mises old is equal to 447. How much was it? 444.47. So okay, so 444.47. So it means we are in the plastic domain, right? And now we have to find out, so we are in the plastic domain, now we have to find out that what will be the new stress value. What will be the new stress value? So for that, what we will have to do is we will have to calculate the DEQPS, so plastic strain rate, increment in plastic strain rate. So plastic strain rate is also given, so you didn't have to calculate it because this is already given. It's 0.002 is the plastic strain rate. So DEQPS is equal to 0.002, right? And then what will be the value of the new strain? So strain increment, we'll have to have strain increment. So this is the plastic strain rate, and in this case you didn't have to calculate the plastic strain based on some incremental plasticity, so tabular format, which we discussed in the last lecture. That was not required because the equation was already given. So where is the equation? Equation should be, yeah, so this is the flow rule which is being followed. So sigma is equal to 10,000 into plastic strain to the power 0.5. Okay, so that is plastic strain. That is plastic strain. That is not rate of change of plastic strain. So plastic strain is equal to initial plastic strain plus the rate of change of plastic strain, because this iteration is going on in this time. So plus DEQPS into delta T, so dt, but dt, let us consider that is equal to 1. So then it will be simply this, and initial value was 0. So initial value, because this is the initial value 440, and at 440 the plastic strain was 0. So this will be 0 plus 0.002. Do we have? No, 0.002. So that is equal to 0.002. And at this strain, what is the stress? So stress nu, and this is Mises stress nu. This is not any other stress. This is Mises stress is equal to nu is equal to, what do we have? So we have 10,000 into 0.002 to the power 0.5. I don't know what is the value of this. Let us see what is the value of this. Control C and Control V. I don't have to put equal to here. So it is 447.21. Oh, the stress value is smaller. How is this happening? Well, so our stress value which we have calculated from the Mises is not converging. So we have to converge it. So we have to decrease the amount of stress. Okay, that is fine. So our new stress value is 44. How much is it? Oh, it is not lower, it is higher. Our Mises is 444 and the stress value is 447.21. So that is good. 447.21. Okay. So we have 447.21. So this is my new stress. And now I have to update stress. In order to do that, I'll have to find a parameter called flow. Flow will be the deviatoric stress. Flow will be Sij minus, we don't have new value of stresses, so it is always old. Sij minus S Mises new, and this whole thing divided by, no, I don't think it is hydrostatic stress. So here it is S hydro divided by S Mises. So this defines the slope, and the new stresses will be the stress mu will be equal to I think deviatoric stress into flow into dEQPS plus, so this will be equal to flow into into S yield, so Mises new plus S hydro. So this will be my new stress, and when I write stress new, it will be Ij, and flow is also an Ij value because this is being calculated for each stress, right? And Mises new is singular scalar value, and S hydrostatic is also a scalar value, right? This is just the mean stress. So this is how my new stresses will come up. And this was there in the coding part where we discussed in the last lecture. Well, not so much was to be done here. In the first part, you just had to calculate sigma Mises. In second part, you had to calculate that what is the new Mises. So if new Mises is higher than 440, that means we are in the plastic domain. If we are in the plastic domain, then what will be the stress corresponding to the strain we have? So that comes out to be 447.21. And if this is my new stress, then how do I update the value of old stresses? By doing this. Okay. So I think that is all. I think question number 1 was that, question number 1A was this, question number 1B was this. Okay, so this is all. Okay.